In this section, we'll learn about the normal probability distribution. Not all random variables take on integer values, like we've just learned about with discrete probability distributions. An example of that would be height, weight, or any other measurement. Theoretically, these values can take on an infinite number of values. Of course, they're limited by the measuring device we have, but theoretically they can take on an infinite number of values. Continuous variables in general lend themselves better to statistical analysis than categorical or discrete variables do. You just have more options of what you can do with them. Graphically, the theoretical distribution can be represented by a smooth curve, and it can also be represented by a mathematical function, similar to what we saw with the binomial distribution, where we had a formula you could use to figure out the probabilities. The total area under the curve has to equal 1, because this is a sample space containing all possible events. The probability that x equals one specific number is 0 in a continuous distribution. This is because a variable can take on an infinite number of values, so the denominator would be infinity, the number of possible values. The area beneath the curve that lies between two values is how we'll have to figure out probabilities. So instead of figuring out the probability that x equals one specific number, we'll figure out the probability that x is less than a, or x is greater than a, or x is between a and b. The normal distribution is the most commonly used continuous distribution. It's also referred to as the Gaussian distribution or the bell curve. This distribution is characterized by the mean of the population and the standard deviation of the population, and these are represented by Greek letters mu for mean and sigma for standard deviation. The formula here is the density function for the normal probability distribution. You don't have to worry about that or knowing anything about it. I just wanted to show you that this distribution does indeed have a mathematical formula that goes along with it, just like the binomial distribution. And one thing you also have to be careful of is not to confuse mu and sigma, the population mean and standard deviation, with x bar and s, our sample mean and sample standard deviation. The normal distribution is bell-shaped and it's symmetric about the mean. That means that if you're above the mean or below the mean, the shape should be about the same. And the spread is characterized by sigma, so how peaked or how flat the distribution is can be represented by the standard deviation. Again, theoretically, there's no upper limit or lower limit, although in reality, depending on what variable we're looking at, there may be an upper or lower limit. The area under the curve has to sum up to 1, again because we're talking about probability. All possible outcomes have to add up to 1. When we take a look at the normal distribution, there's a correspondence between the area under the curve and the probability. So for example, if you look at the area under the curve between 0 and 1, that area is equal to 0.34. That would also be the probability of a randomly selected observation falling between 0 and 1. So the area and probability have a direct correspondence. If you're looking at any continuous probability distribution, the probability of selecting one specific value is always 0. The reason is because there are an infinite number of possible values, so the probability of selecting one very specific value is 0. The probability of an observation falling below the mean would be 0.5. Since the distribution is symmetric about the mean, the probability of falling below the mean is half, 0.5, and the probability of falling above the mean is also 0.5. The normal distribution, again, is described by two parameters, the population mean, mu, and the population standard deviation, represented by the Greek letter sigma. You can also use variance, which, if you recall, is just the squared standard deviation. The mean tells us where the center of the distribution is along the number line. So if you just imagine a number line from negative infinity to positive infinity, the mean tells you where the center of this particular distribution is. The standard deviation tells us how spread out the distribution is. So a larger standard deviation would mean a flatter, more spread out distribution. A smaller standard deviation would mean a more peaked distribution. Just as probabilities associated with the binomial variable change for different values of n and p, probabilities from a normal distribution would change for different values of mu and sigma. So if the look of the distribution changes, then the probabilities change as well. With a continuous distribution, we can't just list out all the outcomes and then find the associated probabilities as we can with discrete distributions. Again, because we have infinitely many possible outcomes. So what we do is find the probabilities of a range. To do this, we would have to know how to do calculus. What we've done instead is someone has tabulated all of these probabilities from a single normal distribution, and then we transform our data into that normal distribution so we can look up probabilities on a table. This one distribution that we'll be using for looking up probabilities on the table is called the standard normal distribution. Any normal distribution can be transformed into a standard normal distribution. The standard normal distribution is simply the distribution that has a mean of 0 and a standard deviation of 1. So the distribution is centered at 0, and then the standard deviation that tells us how spread out the data is 1. So we have to transform our distribution into the standard normal, and then we can use a table to look up probabilities. When we transform any data value into the corresponding value from the standard normal distribution, this is called a z-score. We calculate the z-score by taking the data value that we're interested in, we subtract the mean. This moves the center to 0. So if you take a value, subtract the mean, it'll move the center of that distribution to 0. And then we rescale it to have a standard deviation of 1 by dividing by the standard deviation. So our z-score, again, data value, subtract the mean, and then divide that by the standard deviation. This tells us how many standard deviations from the mean our particular value is. The notation for the standard normal distribution can be noted as either n parentheses 0, 1. That stands for normal distribution. The first value is mean, 0. The second value is 1 standard deviation. Or if we represent it with z 0, 1 in parentheses, that tells us automatically that it's a standard normal distribution. The more general notation with an n can be used with any mean and any standard deviation. So it's helpful to transform our data point into a z-score. Again, it tells us the number of standard deviations an observation is from the mean. And then we can look up probabilities, and we can even compare observations from two different distributions, because putting them into z-scores will allow us to compare them in the same units. Table 8.3, which is posted on Blackboard, gives the area in the upper tails of the standard normal distribution. The upper tail refers to the portion that is above 0. This is just a portion of the table 8.3 that's posted. So when you're working on problems, you may need to refer to the actual table and not to this portion of it here that's in the notes. To use this table, first we have to have a z-score. If you're already given the z-score, you can just look up the probability in the table. If you're given a value of x, the mean, and the standard deviation, you'll have to calculate the z-score by the formula we just discussed. Once you have the z-score, you can look up the probability associated with that z-score in this table. If you look at this z right here, the column gives you the first number and the first decimal point of the z-score, and then this way gives you the second number in the decimal. So for example, if you want to look up the probability of being greater than 1.05, you would go down to 1.0 and then go over to 0.05. So 1.05. So the probability that you would have a randomly selected observation that is larger than 1.05 is 0.147. If you wanted to find the probability that the observation is less than a z-score of 1.05, you would take 1 minus 0.147, since we know that the whole area has to add up to 1. If your z-score was 1.31, for another example, you would come down the side to 1.3 and then go over to 0.01. So 1.31 would be the z-score. We can also use the z-table to help us calculate percentiles. Percentiles can be calculated using the observed data. If you remember when we talked about box plots, we calculated percentiles using observed data. If it's reasonable to assume a normal distribution, we can calculate the percentiles of a distribution using the z-scores. How we do this is we find the z-score of the desired percentile and work backwards to find our value of x. For example, if we wanted to find the 80th percentile, that means 80% of the data values are below that number, 20% are above. Since this table gives upper tails, we find 0.2. So 0.2 would be the percent above that particular data value. So we need to find the corresponding z-score. So if we go over to the side and then up to the top, we can see that our z-score corresponding to the 80th percentile is 0.84. We would then use that z-score and turn it back into the original units using the z-score formula. In summary, if you want to find a probability using the normal distribution, first you draw a picture and shade the area corresponding to the probability you want to find. Second, you calculate the z-score or scores if needed. Sometimes you're already given z-scores, so you wouldn't need to do this. If you're given x, a mean, and a standard deviation, you would need to do this. Third, you look up the probability in the table. And fourth, you check that your answer from the table makes sense with the picture that you drew. For example, if the area that you shaded is less than half of your graph and your probability is greater than 0.5, then those don't match. So you would know you need to take 1 minus that answer to get the correct probability. If you want to find a percentile using the normal distribution, you first draw a picture and shade the area corresponding to the percentile you want to find. Then use table A.3 to find the z-score associated with the upper tail probability. So this is when you find the probability in the inside of the table and then find the corresponding z-score. Then you convert the z-score to the original units. So x equals z times sigma plus mu. So we're just using that z-score formula and solving for x. Then again, you check that your answer makes sense with the original distribution and the picture that you drew.